All right, welcome. Today we are talking about tangent lines and rates of change. So this is our first topic as we are sort of delving into our introduction to calculus. These concepts should actually be pretty familiar. We just might be using different terms than maybe what you're used to. First thing, rates of change. Basically, rates are just sort of comparing two quantities of different kinds. In other words, we're measuring like how much one variable changes in relation to another. So you have some examples over here of the rates. Notice the units on rates are always something like errors per page or runs per game, goals per game, runs per test, whatever. It's always something per something. So the most common one that we probably think of is miles per hour, talking about speed. So a lot of these are going to come back to that. So let's look at an example. Kristen's pulse is measured at 67 beats per minute. So we know we're dealing with a rate. We want to explain exactly what this rate means. Well, per meaning every time 1 minute transpires, she beats her heart, or her heart beats rather, 67 times. So we can just say that her heart, let's say Karsten's heart beats 67 times each minute. And so how many heartbeats would we expect to have in an hour? Well, if my heart beats 67 times in 1 minute and there are 60 minutes in 1 hour, I'm going to do 67 times 60, and that should give us 4,020. And when we're dealing with these types of things, we always want to include a unit, so that is 4,020 beats. All right, I will let you work the next example, or problem number 3. Let's take a look now at average rate of change. So we looked at the basics of rates. An average rate of change just means basically how much did your variables change over the course of a given interval or a given set of time. So if we are looking at this table here, we want to find the average speed from first Tilem Bend to Neil, and then from Horsham to Melbourne. So I will do part A. I will leave part B for you to do. But basically, we're just going to figure out how much distance was covered and how long it took to cover that distance. So if we are going from Tilem Bend to Neil, well, we started counting at 98 kilometers, and we stopped counting at 324. And then on our time scale, we started counting at 63, and we stopped counting at 204. So if we simplify that out, in a fraction that's 226 over 141. If I reduce that into a decimal, or convert that into a decimal rather, that's 1.602 kilometers per minute. So we covered 226 kilometers every 141 minutes, therefore 1.602 kilometers per minute. I will leave part B for you as well as example 3, or rather problem 3. So now let's look at an average rate of change as given on a graph. So basically what we're going to do to figure this out is we're going to connect the starting and ending point of our interval and figure out the rate of change between those 2 points. So again, I'm going to do part A. I will leave parts B and C for you. This says to find the average speed across the first 4 seconds. Well, I'm starting counting at 0. If I stop counting at 4 seconds, that would be about here. So what we want to do is connect the 2 points and figure out how much we changed on both our x and y axis. So this we can approximate at about 0, 2. Let's see, this guy we can say is definitely 4 on the x-axis, and let's, again, we're approximating, so we'll say that's 2.5 on the y-axis. So, we went from 2 to 2.5 on the y-axis. We went from 0 to 4 on the x-axis. So if we take 0.5, divide that guy by 4, 0.125, and again we have to pay attention to our units. So we traveled 0.5 meters in 4 seconds. So our units here are meters per second. All right, so go ahead and do the same thing on B and C. We've got one more example to look at today, and that is instantaneous rate of change. So instantaneous rate of change basically means how fast are you going right now, not over the course of your trip, not over a specific interval of time, literally right now. If our line is perfectly straight, it's easy to tell because we're counting up the same number of units as we are counting over at like every interval. However, if our line bends, we can't simply count the spaces because the speed is changing at every spot. So what we need is some sort of approximation, something that flattens out to look more like a straight line. And so for these types of problems, they're going to have to give us a point that we are looking at. Notice they're saying use t equals 1. So what we're going to do is sort of attempt to flatten this curve out. Give ourselves a nice little line. So we will notice that the line we drew hits the curve that they gave us at the point that they labeled. Anytime a line touches a curve at exactly one spot, that is called a tangent line. Do not confuse this with sine, cosine, tangent trigonometry. This is similarly related, but it is not the same thing, okay? We are simply saying that the line touches the curve at exactly one spot, as opposed to passing through the curve that we saw with the average rate of change. So anyway, we have our tangent line. We can use this tangent line to approximate the rate of change of the curve, or of the original curve at the spot we were looking at. So just like before, we are going to sort of approximate these points. So that appears to be about 0, 1. This appears to be about 2 and 3. So now I just need to figure out my rate of change. So it looks like on our y-axis, our distance traveled, we went from 1 to 3, and it took us about 2 seconds to do so. So we are traveling at approximately 1 meter per second. All right, that is all I have for today. I will see you next time.